When we write a recursive function, like this one in plate notation, we are at some level creating a cyclic data structure. Somewhere in the plate implementation, there's a representation of this procedure that is able to refer back to itself. And we can see this more clearly if we look at the data structure that represents a curly function, that same example in curly notation. There would be a closure that says the argument name is x and the body is f applied to x in an environment, this is the environment part of the closure, where f refers back to the same closure. So there's this binding that's inside of the closure that has an extended environment that has a binding that refers back to the same closure. It's a cyclic data structure. And we can look at, more generally, what sort of cyclic data structures we're able to construct with Letrec. In Plait, we have boxes, for example. Let's define B to be a box. And inside of a box, we could put another box. So if we make B that has there's a box with a box inside of it where that other box has false, then when we evaluate the definition and look at B, it prints out this way. It says there is a box that has inside of it a box that has inside of it false. Now since it's a box, we can use setBox to change what's inside of it. And could I put the box itself back inside? Well, the type checker doesn't allow this because the types don't work out. Let's ignore the type checker for now. I'm going to use the #untyped tag here for a plate that turns off the type checker. I'm going to define the box, and then I set the box. And now if we look at B, what we see is some even stranger notation. So the middle part here says that it's a box. And inside of that box is a #0 hash. But #0 hash refers to whatever #0 equals defined. This is some more notation inherited from Lisp. But what it means is it's printing a cyclic data structure. It's a box that has inside of it the same box. And we can see that also if I do unbox of B, I find out what's inside of B, I get exactly the same value, which means I could unbox that value and so on. And we could call unbox as many times as you would like, and we're going to keep getting the same value. So that's an example of a cyclic data structure. I didn't write it with Letrec. In fact, if I try to say Letrec B is box B and return B, then I still get that use before definition, use before initialization error. So it turns out that Letrec is not powerful enough to implement this kind of data structure, this kind of cyclic data structure. But there is another form in Plait. It's called shared. And shared is a kind of generalization of Letrec that lets us, in certain cases, refer back to the thing we're defining, even though Plait would not normally delay the evaluation of that expression. So if I use shared instead of Letrec, then I get the same thing. And then with that shared box, no matter how many times I unbox it, I'm still going to, again, get the same thing. Now, boxes that go to nowhere, boxes that go to boxes that go to boxes that keep going nowhere, that doesn't seem very interesting. But more interesting might be an infinite list. Like, what if we want to give some process an infinite list of numbers where the numbers just count up? Right? That might be an interesting thing. Let's see what we can do with shared for that. So I want to say shared, make a list where I'm consing 1 onto the list L. And then I'm just going to return L. We'll see that this works. So shared is making an infinite list of 1s. It prints out in a funny, even funnier way. It says it's a list where the first item is 1, and this dot means the next thing I'm going to show you is not the second thing in the list, but it is the rest of the list. So the rest of the list here is #0 hash, which is the same list. So if I did rest of L, then I would just keep getting the same list because L's rest is itself. Another thing I can do is use listref to get an element of the list. So if I do listref L0, then I get 1. If I look at the next item in the list, it's still a 1. If I look at the 100th item in the list, it's still a 1. L is an infinite list of 1s. No matter how many steps I try to look in that list, I will get the same answer L. So shared is a kind of generalization of Letrec that can make more kinds of cyclic data than just functions. It does have some limitations though. For example, I can't say, it should be equivalent to say first of list of L, since first just takes the first thing of a list and list makes a new list, so that should be equivalent to just L, but in fact shared cannot deal with this pattern. Shared is a kind of generalization of Letrec, but it's still constrained at what kinds of things it can handle syntactically on the right-hand side of shared. To make this kind of example work, we need to generalize even further. We need to somehow, for any kind of variable reference, delay that variable reference until it's actually needed. And then we can write arbitrary shared data structures like this. But to do that, that will be our next step, looking at lazy languages.